Hello there. Let's look at bond dipoles, dipole moment, polar and nonpolar. You want to get started with something like this one, methane, the nonpolar molecule. That's a typical example. Now also a good idea to know something like CO2, the linear molecule, also symmetric and nonpolar. Now imagine if you replace one of the oxygens with something like sulfur or selenium, something like that. So what happens? You lose the symmetry, right? And because of that one, it's going to be polar. So that's the logic you're trying to understand. And how you do that is because look at the electronegativity pull to the carbon to the sulfur and carbon to the oxygen is different. Therefore, these two do not cancel. So dipole moment is not zero, therefore polar. You see three steps. Bonds dipole, dipole moment is not zero. It gives you a polar molecule, right? And now you can also compare extreme scenario like HCN. So the C to the H pull and the C to the N pull is different depending on the electronegativity. Therefore, the dipole moment should not be zero. Therefore, it should be polar. So you see asymmetric by the look, polar, and then you can explain with the bond dipoles and the dipole moment, which is the sum of it, right? Now, like I said, the moment you see, you want to look at the symmetry and decide polar, non-polar. And then also remember always, when we're talking about polar, it should be dissolving in the water. So it should remind a little bit of a delta minus delta plus of the water, right? And no question, if it is ionic, there's plus and minus, right? So we do have some ionic examples. Now, on top of everything, the the pictorial, you have to think, is it symmetric or is it not symmetric, right? So those are the things you want to think and draw and illustrate, right? So, what they say, pictures speak thousand words, right? So that's what it is basically. Now, we can look at simplified version of polar versus nonpolar molecules, right? So there's a bunch types or classification you can use, and that just for commons. You see, I don't really recommend memorizing examples though, right? See, symmetric one is BeCl2, and when you change one Cl to something else like fluorine, and that is not symmetric, right? That's the logic you're trying to understand. Same thing, CH4, symmetric. You cut one hydrogen and put something else like chlorine, and it will be CH3Cl, right? So that's how you're trying to understand, not by memorizing everything. Okay, now we also can take any inert gas. What's the inert gas? The noble gases: helium, neon, argon, krypton, xenon, radon. All of them. These are single spheres, right? Little balls, and they are perfectly symmetric. So therefore, they should not be polar, right? Then jump to the diatomic molecules. What are the diatomic? H2, N2, F2, Br2, I2, that kind of things. Of course, it's like two solid balls come together, two spheres come together, right? So they are symmetric too, because you can cut through the middle line, right? So that's what, so solid one ball has or one sphere has many symmetries, and then if it is stick by a two balls with a stick, that would be having a symmetry too, right? So that's the idea. So the all basic shapes, next one. So monoatomic, diatomic, and then all basic shapes, all basic geometries. What's that? Remember that types: AX2, AX3, AX4, AX5, AX6. So that's like two-legged dog, three-legged dog, four-legged dog, and so on. Now, what happens here? Actually, boron to fluorine has a pull based on the electronegativity, but these are like three horses pulling away and same energy, so it cancels out. So that's why the dipole moment becomes zero, and therefore it's nonpolar. And also you can see symmetric, nonpolar, voila, right? Now compare the linear molecules like fluorine to fluorine with HCl. Just remove one fluorine and put another Cl. So now it's not symmetric. Voila. So again, it's gonna be, let's talk about the bond. The bond is dipole, right? One side is more electron density, the other side is less. So you can actually mark it. Now, the sum is only one there, so dipole moment is not zero, so therefore it's polar, right? Now see, you recognize the asymmetries and then you can say it's polar, right? Now look at this one. So boron in the center, trigonal planar, but fluorine, bromine, iodine pulls in three different energies, right? Fluorine has the highest pull, actually, electronegativity pull. So therefore, bonds dipole, and the sum of all these dipole moment not going to be zeros. Look at that one. So some of them are powerful, right? So therefore, there is a imbalance in the electron cloud. So therefore, it's polar molecule, right? Because it's not symmetric again. You see, every time I kind of go back to the same thing. So it's the same mantra actually, right? So now, the other most popular question your prof would like to ask or your teacher would like to ask is ammonia versus water. This is a really good one to know, right? Because that's important and that's right a really valid logical question to ask. Look at nitrogen. On nitrogen, there's one lone pair, and on oxygen, there's two lone pairs. You want to think about the lone pairs in these two cases. Why? Because you see the pull between nitrogen to hydrogen. Well, I mean, towards the nitrogen is one pull go together, and the sum of the vectors go push upward. So therefore, the bonds are dipole, and the dipole moment is not zero. Therefore, it's polar and it's not symmetric, right? And look at the water, the hydrogen to oxygen, there's a push and push. The sum of the vectors pushing upward more, so therefore dipole bonds are dipole, and dipole moment is not zero, therefore it's polar, right? And CCl4, CH4, they are symmetric, right? If it is symmetric, everything cancels out. The bonds are dipole still, but the sum will be zero, right? Bonds are dipole, and dipole moment is zero because they cancel each other. Four horses pulling same power into four different sides, right? So it's non-polar. Now, so yes, I was asked a few questions about the cheat sheets and you know how to keep things together for the exam, and how to easily memorize and understand in a way and regurgitate in a way, right? And there are challenger questions you have to work harder, but there are questions you can just get it like that, right? Now look at this one. How do you do that? So do these two columns, the type and the electron domain, right? Now, um, the first thing, AX2, you know, the spread as much as possible because of the electron repulsion. It's 180 actually, right? And then it's linear. So 180 degrees linear, AX2. Now AX3, you put another sort of jack up another x into the AX2 and you get the AX3, right? Now these ones are equally separated circle, that would be 120 degrees, and then this has to be trigonal planar in single plane, right? So that's how kind of you build that your cheat sheet, right? Logically. Now AX4, you can see the first one, you jack up the X into the bottom. Now you put into the top so that you'll get actually AX4, right? So you should hit this one from the front or back. So when you have front or back, solid one means coming out of the screen, the dashed yellow going into the screen. Of course, the bond angles are identical, 109 and tetrahedral, right? So the tetrahedral question, so I got few questions about that one, how to understand. Actually, understanding carbon's tetrahedral is the most important thing. So look at one plane between three x's is one plus, and then the other plane downward, that's a second plus, and then blue plane between the three x's, that's the blue plus, right? And then the white plane, which is everything back there, right? So that's how you get four planes. That four planes gives you the tetrahedron, and which is tetrahedral. So there's another way actually you can draw them. See, you plane one plane, three sides, three atoms, x's, and the other plane, and now it's like a triangle. Now you have a bottom and you have a back of white, right? So that back side. So that's the four sides. And just take a piece of paper if you have trouble seeing it, and cut four pieces of it, triangles, and stick together, right? Okay, so let's clean this one so you can see still the tetrahedral should be shown this way. So the AXX, the green ones are on the screen, and then the yellow ones are going up and down on the screen. Now, the AX4, this is AX5, so let's correct this one first. So AX5, so you have a 90-degree angle from top to the bottom, but within the triangle is 120. So always remember the triangle is cutting the circle into three, so that would be 120, right? Now you can draw a pyramid to the top. Okay, if you can draw a pyramid to the top, and also you can draw a pyramid to the bottom, right? Because it's a triangle base. That's why it's a bipyramidal. And the base is trigonal, so you call trigonal bipyramid. You see how you build the bipyramid? So one pyramid to the top and one pyramid to the bottom, right? And its base is triangle. That's why it's trigonal bipyramid, right? Now the next one is AX6. Let's correct these the groups, right? So AX6 would be, so let's fix this thing. This is AX4, AX5, and AX6, the last one, right? We can get rid of these shapes, so you can practice. You have to practice. That's how it works. Now, so AX6 is you gonna put another X from the side. So now the triangle plane mid becomes a square. You see that? So that's the square. In a square, you cut into four, and that will be 90 degrees. See, that's the square. You cut into four, and this square you can push upward, and then you have four sides to the top, and the blue four sides to the bottom. Now, 4 and 4 is octa. That's why it's octahedral. So basically, you have 8 planes. That's why it's octahedral, right? So this is a good example to compare the octahedral with the tetrahedral. Okay, so those are the fundamental shapes, and they are actually symmetric, and they will be nonpolar when they are same kind atoms sitting there, right? Well, center could be different, but all the sides should be the same to be nonpolar. Now, like I mentioned this one in the question, so the ammonia versus water has to be completely compared side by side. So CH4, AX4, 109 angle symmetric, and it should be, yeah, you can compare ammonia to this one. So because our typical molecule is CH4. Now remove this hydrogen and put a lone pair on the nitrogen because ammonia has a lone pair, right? So then AX3, the hydrogen's 3, and then lone pair is an big E because it's electron pair. That's why it's big E because it's more than one electron, right? And your 109 become 107 because the lone pair on the head in the pink, which is pushing down, so the angle becomes smaller. Now go to the water. So draw the similar molecule like CH4, but these two will become lone pairs. Now E2, the lone pair, and then what is AX2? H2O, right? AX2. So now here 4 electrons pushing so hard the hydrogen, your angle will be 107 becomes 105, and it's asymmetric and it's polar. So now you see your angle change. One lone pair will become 109 to 107, two lone pair 107 goes to 105. See the order. Now if you can draw that one, you can talk about water polar dissolves everything and it's 0 degree melting point, and then nitrogen is ammonia is about some minus 78, and then so yes, the other question here, the compare ionic covalent network covalent bonding and properties based on that one. That's another cheat sheet, maybe 5 minutes. Try to do that and answer the questions. The other question, yes, here the compare sodium chloride to lithium chloride and magnesium oxide to magnesium sulfide. That's about the lattice energy. So try to do that. Thank you.